So Winnow algorithm, right? So we will come to it. Before that, we need to talk about. Uh, we have already discussed quite a bit about monotone disjunctions, k monotone disjunctions, right? And then in the end of last lecture, I said that if it is a monotone disjunction, it means that you can draw a line in an input space where all your data points are, such that all the points that are labeled by that monotone disjunction will be on one side, and all the points that are labeled as negative by that disjunction are on the other side. So let me do a quick analysis of that, right, with an example. Okay, so let's consider an example where your data is represented using six-dimensional, so using six attributes. So this is, let's say this is the tumor example, right? So let's say you have six attributes, d equal to 6, which means, and each attribute is binary, of course. So let's represent them as x1, x2, x3, x4, x5, x6, right? Each one of them can take two values, right? This could be 0 or 1, 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 right? So just as a notation, we can also denote these either as bit vectors, 0, 0, 1, 0, 0, 1, things like that, or I can also represent them as this. So if it is x1, then it means it's x1 took a value 1, and if it is x1 bar, that means x1 took a value 0. All right, just this is just for notational convenience, so please don't get confused. All right, so let's go to lines now, right? So we're talking about lines. Now, what is a line? So a line in two dimensions, right? So if you think of a two-dimension coordinate space, a line can be represented by connecting 2 points, right? So in geometry, you might have seen the expression of line in different ways. So a very popular one in math is you write it like this: y equal to mx plus c. M is the slope, c is the intercept, right? In our case, just to keep it consistent with what we have seen so far, we are going to denote our axes not by x and y, but by x1, x2. So this essentially we can write it as x2 equal to mx1 plus c. So that's one way to write an equation of a line. The way we are going to denote it, because that is easier in machine learning, is we are going to denote it as a coefficients multiplied by the coordinate, each coordinate equal to some constant. Okay, so an equivalent notation is w1 x1 plus w2 x2 equal to something, theta, right? So theta is a scalar. That means theta belongs to just r. All of these are scalar values, real numbers, right? So this is another way to represent a line. Okay, when we move to 3 dimensions, so in 3 dimensions you will have x1, x2, and x3. So now when you think of a line, it's no longer a line, it's a plane now, right? So in 3 dimensions, so if this is your 3-dimensional space, then this could be if I hold it straight, this could be a plane that we are interested in. And 4 dimensions, after that we can't see it, but we call them hyperplanes. All right, so so remember that. All right, so which means that for our example, if we want to draw a hyperplane, we can represent it as an equation which looks like this. Okay, theta can be anything, right? So what does it mean? So these constants here, right, these are all getting multiplied by your attribute values. All right, so in our in machine learning we call these attributes, in geometry we call them coordinate axes. So they right now in our analysis they mean the same thing. All right, so the first thing I want to tell you is that assume that your k monotone disjunction, right? This is your disjunctive concept is like this: x 3 or x5 or x6. This is a valid k monotone disjunction if your k is 3 or more. Now what does this mean, right? It means that it calls any data point as positive or malignant if its third attribute is 1, or the fifth attribute is 1, or the sixth attribute is 1. All of them could be 1, only one of them could be 1, it doesn't matter. At least one of them has to be 1. That's the notion of a disjunction, right? And we don't care what happens to the other one. So x1, x2 and x4 can take any values. They could be 0 or 1, right? So now if I say that let's write an equation of a line, consider this line. W1 equal to 0, W2 equal to 0, W3 equal to 1, W4 equal to 0, W5 equal to 1, W6 equal to 1. So consider this hyperplane. When I say this hyperplane, it means and theta equal to half, right? So the equation of the line will be 0 times x1 plus 0 times x2 plus equation of the plane will be 1 times x3 plus 0 times x4 plus 1 times x5 plus 1 times x6 equal to half. These are all products, right? So I'm just giving you this hyperplane out of my hat. So what will happen is that any data point which is classified as positive by this rule, this concept, will lie on one side of this hyperplane, and any data point that does not will lie on the other side. Okay, so let us think about it a little more. So the claim that I'm making is a point, right? A point which is essentially a 6-dimensional vector, binary vector, that is classified as positive by C, which is this one, will lie on top, or yeah, above. Sometimes we say above the line, the plane, this plane. All right, this plane. Any point that is classified as positive by C will lie above the plane, and any point that is classified as negative will lie below the plane. All right. So now, yes, go ahead. No, this, yeah, that's a good question. So this, I'm just saying that let's assume these are the values. I'm just right now pulling it out of my hat. Later, we'll figure out how to learn these ourselves automatically. All right. So when I say above the plane, it means that, all right. Okay, just for another notational simplification, we also write this equation in a vector form as this, W transpose X. I try to make this bold, which means this is a vector which contains all of these values, and X is a vector. So let W be a vector which is W1, W2, W3, W4, W5, W6, right? So this is essentially just a vector, and X is your input data vector, which is another vector of 6 values. Okay, so another way to write this line is W transpose X equal to theta. When I say transpose X, we also call it a dot product or an inner product, and I told you last time what it means, right? Okay, so when any point that is above the line, for that what will happen is W transpose X will be greater than theta. Okay, and anything that and otherwise a point that is classified as negative by C will lie below the plane. That is, W transpose X will be less than theta. All right, and of course, since this is the equation of the line, which of the plane, it means that if x lies on the plane, then W transpose X will be equal to theta, because that's the equation of your plane, right? Any questions so far? All right, so I'm going to just not move it away. Keep it here. All right, okay. So carrying on. So just a side detour. So what does it mean for any object, right? So the next question that you want to think about is, what does it mean for C to classify a vector X as positive or benign or malignant or belongs to the concept, right? What does it mean? It means that at least one of these three values will be 1 in X. Yes, go ahead.
So situation should be like W transpose dot product X and then put the data.
Yeah.
And the situation has not what does that represent?
What is?
Good and positive, less than negative. So F equal to theta. What does that mean?
Oh, if W transpose X is equal to theta, from geometric perspective, it means that that point is on the plane, right? From machine learning perspective, that's sort of an ambiguous setting. There you would have to probably decide arbitrarily. You say, okay, if it is, I mean, I could have put it equal to theta here and then call it positive. But that's a good point. That's sort of a situation that we'll have to figure out by an arbitrary decision. All right. So what does it mean for C to classify X as positive? It means that at least one of X3 or X5 or X6 is 1, right? Because if none of these are 1, then this rule will call it negative, right? Because it will find all of them as 0. So at least one of these is 1 and others could be anything, right? And the same way, that's question number 1. Question number 2 is, what does it mean for C to classify X as negative? Which means that, yeah, all three of X3 and X5 and X6 are 0, right? If they are not, any one of them is 1, then it will be called positive, right? So is this clear? That's sort of the definition of this concept, right? Okay, so which means that if I go back to this equation, right, then if a data point belongs to the concept, it means it's positive, it means one of these will be 1, right? So when I multiply it with 1, then it will be 1, right? And everything else will become 0, which means that for a positive instance, the value of W transpose X, so W transpose X for a positive instance will be greater than 1. Greater than, it could be 1 if there is only one of them as positive, but it will be at least 1 or more. Right? Is that clear? And so that's one important point. And then what will be W transpose X for a negative instance? It will be 0, because as I said, a negative instance, all three of them will be 0, and only their weights are non-zero, right? All other weights are 0. So even if other attribute values are 1, they will get multiplied with zeros and it will become 0. And only the values that are on the weights, the positive or the 1 values are the ones for which the instance values are 0, right? Yes, go ahead. No. Yeah. So we are right now talking about the instances. So remember that our concept is this. This we have fixed. This is not changing. So this definitely is a disjunctive concept, right? Now what we are trying to see is that is a new data point X will it be classified as positive or negative by this? So only those instances will be classified as positive in which at least one of them is 1, and only those will be and all those for which all three are 0 will be classified as 0. All right, so that's the point, which means that I have an equation of a plane here, right, such that it can divide the data point into two parts, right? That was what I wanted to sort of prove in the beginning, is that if your concept is a k-monotone disjunction, then you can come up with a plane such that it will split your or it will divide your space into two parts such that all positive parts will be on one side, all negative on the other side. Yes, go ahead. Where did we use it? So far we haven't. So listen, sorry. So remember, we have not yet come to an algorithm, right? Right now I'm just trying to say, now the next point will be that we'll come to the algorithm. So the question was that so far we haven't really used the notion that it's disjunctive concept, but actually we are going the other way. We first assume that it's a disjunctive concept. From that we understood that there is a property like this, that there will be a line. And now we will try to come up with an algorithm that will learn that line. Okay, and because it's a k-monotone disjunction, it means that that line will be able to predict the points correctly. So that's the process of our thinking, right? All right, so equipped with this knowledge, so now the next question comes is how to learn this W from training data, from D, right? Because earlier I just arbitrarily told you that consider this plane, right? But if I just give you some training data, then you cannot because we were able to come to this hyperplane only because I knew the concept, right? I just set these values as 1 because I knew the concept. But what if I don't know the concept? Then how do I learn this value? And that is what the algorithm called Winnow will do. All right. So between the two of you, your questions basically set the whole stage. So the first question was, how did I arbitrarily come up with these weights, right? The reason I came up with these weights was because I knew what the concept was. Because the concept was this, I set those corresponding weights to 1. But we cannot, in real setting, if I just have the training data and I don't know the concept, then I cannot set them. So there is where I will use the notion of disjunctive concepts. Okay, so now let us look at the Vino algorithm. Oh. All right, we looked at all this, right? This is more of a figurative, and we have gone through this a bunch of times. All right, so this is the Vino algorithm. Okay, so first thing, let's just look at it step by step, but then we'll do more of a hands-on example. So the way Vino algorithm works is it first sets theta to d by 2. Okay, that's just a choice. D is the number of attributes you have, right? So if you have 6 attributes, then theta will be 3. Then it essentially has to learn these weights, right, to then classify things into positive or negative. So it assumes, in the beginning, it assumes all weights to be 1. Right? It says that all the attributes are part of the disjunctive concept because it doesn't know anything else, right? And slowly, over these iterations, it will slowly remove the non-essential attributes. So remember that if we go back to our example, we want to learn this, right? We want to learn that this is our weight vector, because if this is our weight vector, then we essentially know that this is our concept, right? So in the beginning, what it does is it sets all of these to be 1, and then slowly what we will see is that it slowly makes these 0, the ones that are non-essential, and then it will be left with other 3. All right, so that's why it's called winnow, because slowly over iterations you are sifting away all the unneeded things, and you'll be left with what you need. All right. All right, so let's go through the algorithm again. So the for loop starts on line number 3 is basically your online learning. So every loop means it is looking at one training example. Okay, so the first thing it does is it takes a training example and it applies this rule. Okay, so this is a classic online learning setting, right? So it applies this rule, which is it computes W transpose X of I, means it's the ith example. So these both are vectors, and then you compute inner product, then it checks if it is greater than theta or not, right? Because that is its prediction rule. So if it is greater than theta, then it calls it as a positive example or 1, otherwise it calls it negative or 0, right? So this is the prediction part. The next thing it does is it checks if it has made any mistakes. So if the real, this is the real this is the actual label, and this is what you predicted from here. If they match, then you don't do anything. That means you're fine. But if it doesn't match, then you update your weights. Now you update your weights in 2 ways. So depending on what was the true label, so if it was positive, then you essentially, what you do is you bump up the weights of all those entries for which the input instance was 1, and I'll come to the details a little later. And if it was a negative, then you basically bump down to 0 all the weights that were 1, and you keep going this way. All right, and so without telling you anything else, the idea is that over iterations you keep refining your weight. Okay, and hopefully at the end of training data, the weights that you will have would be able to correctly classify the objects into 2 classes. All right. Okay. So briefly, what happens is every time a mistake is made, you move the hyperplane. All right. So because we are changing W, right? So think about a line again. So when I said a line is W transpose X, so it essentially gives you a line, right? Or in 3 dimensions, it is this plane. If I change my W, these are parameterized by your W. If I change my W, the effect it has is that it rotates it, right? So that's what is happening here. So every time you see a new point, you make a mistake, you rotate your line, and then you will be left with the right line. All right. So let's do a quick example. Let's do it here first. I also have a Python code to show how it works, but let's do it this way. Okay. So we're going to make some assumptions, things that we don't know, but we assume that our real concept C is x1 or x2, and D is equal to 2. So this is a 2-dimensional case, just for because it's easier for me to draw. So there are only 2 attributes. This is your true C, right? Now, how does Winnow work? First, so the W that it wants to learn has 2 values. So let's call it a vector. In the beginning, I initialize it to 1. Both are 1, right? Now, let's say the first training instance that I get is x1, x2 bar. All right, and of course this is positive. This is positive or 1. So this is the label, and this is the x. So this is the first instance I get, right? So what do? I compute its W transpose X, which essentially means that I am doing a dot product between 1, 1, and this would be 1, 0, right? 1, 0, right? So what will be the answer? 1, right? So we set equal to 1, and of course theta we have set to d by 2, which is equal to 1, right? So here is when we check. So this is our prediction. So this is what we call C of X. in the algorithm, I also have a subscript to denote which iteration it is. So for the first training instance, this is my prediction, right? And the C star of x of 1, the real label, of course, is 1, right? Which means that you have no, so there's no mistake, right? So you don't do anything. So let's say the second instance, second training instance, is x1 bar, x2 bar, right? And of course, this one will be negative because it doesn't agree with the the concept. So negative or minus or zeros, right? So now what does happen? Your W is still the same, theta is still the same. Then you compute C of x of 2, which is your second instance, and that will be 1, 1 transpose. This is 0, 0, right? So the answer will be 0. And but this, right, this one, sorry, I'm a little confused. Right. So, right. So now what happens is that your C of x of this is actually is 0. So there is no mistake again. No. Yes. Where, for the second example? No, but here I'm assuming these are x1 bar, x2 bar, which means they're taking the value 0 and 0. If it is 1 and 1, it will be x1, x2. That will again be positive. I took a very wrong example. Basically, this would not change at all, but that's because you already are at that concept, right? So, so just to finish the discussion, I will still carry on, right? So there will be no mistake. So you don't change your W, and then you get the next data point that will be C of x3, and that also will be right, and this will be 2, and C of star of x, sorry, this is 2, which is greater than, I'm sorry, there is also a comparison to theta, so that means this is equal to 1, right? It has to be greater than theta. And then C of x star of 3 is also 1, so no mistake. And I won't do the fourth one, but what you'll see is even in the fourth one, there is no mistake. So at the end of it, you have gone through your training data set. In this case, your training data set basically was all of your data. But at the end, you didn't update your weight at all because you started with the right weight. So you were lucky. Go ahead. This is the C, this is the true label. Right, so this is also given to you when you're training. These are the labels, right? I want to do another example where it works in a different way.
Does it matter that the first and fourth example are equal to theta?
Yeah, the output.
Right.
It would matter, but in this case, if you remember, in our decision rule, we took the equality up here. We said if it is greater than equal to theta, then it's 1. That's why. If you change it, then it will matter again. Okay. All right. Let's consider another example. I'm sorry about that, because in this one we couldn't really see how Winnow was doing. So this time let us assume that C is actually x1. So anything with x1 will be positive. All right. Anything in which x1 is 1. So what does Winnow do? So let's assume the same training data. This is your x and this is your C star of x of I, and this is x of I, and of course this is I. So 1, 2, 3, 4, x1 or x2, x1 bar, x2 bar, x1, x2 bar, x2, right? Of course these one will be positive. Anything which has x1 will be positive, anything which does not have x1 is negative, right? So this is your trading data, this is your day. So what you do is first you set your W equal to 1, all ones, and your theta is again d by 2 equal to 1, right? So the first instance comes, your C of x of 1 will be this W transpose x if it is greater than theta, right? So this is the row. So W transpose x will be 1 1 times, so let's call these 1 0 0 0 1 1 and 0 1, right? This is a binary way of writing the same thing. So when I do 1 0 times 1 1, it gives me 1. 1 is greater than equal to theta, so the prediction will be 1. So this hyperplane right now will call this training instance as 1 or positive, and so you can also call them 1 or zeros, and C star of x of 1 is also 1. So there is no mistake. So you do not change your hyperplane at all, right? Now comes the second point. The C of x of 2 will be dot product of this with this. So that will be 0, right? And 0 is not greater than theta, which means that C of x of star will be 0. You will call it a negative example. And C of star of x of 1 is also 0. So no mistake. Now comes the third one. Right. Yes. Right. So what did you say? How are we? Right. No, if I say that it is concept is x1, that means that value of x2 doesn't matter. So that concept will call any any data point which has x1 as true or plus 1 as positive example. Or these are disjunctions, right? So it's always or, yeah, yeah. So that's why we call that positive, right? All right. So no mistake here either. Just for our fun, let's assume that this is our training data. So the third point is this one, okay? So the third point is, so let's compute what is C of x3. This is 3. So third point is actually 0 1. So when I take 1 1 transpose 0 1, that will give me a value of 1, right? Now 1 is greater than equal to 1, that means that this one will be 1. So C of x3 will be equal to 1. However, C star of x3 is 0, right? So that's where the mistake is. So which means that we need to update our weights. All right. So the way the weights are updated is they are done in two ways. So it depends on if the actual example was positive or negative. In this case, it was negative. So you made a mistake on a negative example, which means that if you go back to the algorithm, we will demote, we will set the values, those values in W to 0 for which the training example was 1. Okay. So which means we call these eliminations. Eliminate all those entries of W where the input X is 1. Okay, so that's kind of in words, this is the rule. So, which means that, see, this was your input X. The input X was 1 here, right? So we will eliminate. So now your new W will be, we will just set this value to 0. So this is your new W. All right. So this is how Winnow would work in this case. Now, there's also this notion of a promotion, right? Which is, if your mistake was on a positive example, if this one was positive, then what you would have done was you would have doubled the values of W wherever input was 1. Okay, so that's how it works. So now let's try to understand. Any questions so far? Yes. Doubled in the sense we set all those entries, remember here? Oh, well, actually we said set it to alpha times Wj. So all the entries for which Xj was 1, you multiply it with alpha, and typically we set alpha to 2. It has to be greater than 1. We set it. So that's what I mean. We promote those values. So essentially what we are doing, so if you think about it, right, it works in a very interesting way. So every time you make a mistake, there are two types of mistakes, right? You have made a mistake either on a positive example or on a negative example, right? And in each case, you do something different. So let's sort of try to understand that. And then when you do the gradients problem, it will also make it a little more clear to you, right? So what does a mistake mean? Right? So there are two types of mistakes. So mistake number 1, mistake of type 1 is that we predict X as positive when it really was negative. Right? And the mistake of type 2 that we predict X as negative when it really, when I say when it really was positive, it means that its true label was positive, right? So there are two types of mistakes, and in each case we are doing something different, right? When it is this case, we do what is called elimination. That is, we set all the 1 values to 0, and when it is this case, we call it promotion. We multiply those values. So what does that mean? So let's sort of try to understand it, right? So when this type of mistake happens, it means that you called something positive when it really was negative, right? Which means that that instance, what you know about that object is that since it's a negative instance, it means all of the entries that belong to the concept, right? Remember, the concept is a disjunction of some fewer entries. All of those entries are 0. That's what you know about that point, right? But you are calling those entries as, you are calling that point as positive, right? That means that you need to lower the effect of those 0 entries, right? Because what each element is telling you, what X tells us when C star of X is 0 is that all the entries, when I say entries, all the attributes that are in the disjunctive concept are 0. Right? We don't know the disjunctive concept, but because we know that this instance is negative, it means that all of the things that are in the disjunctive concept have to be 0. Right? So that is why what we do is we set all of the ones that are 1s to 0, which means that what we know is that since all of them on an elimination, none of the attributes that are in the concept none of the weights for attributes that are in the concept will be set to 0. You see what I mean? Because these ones, these entries will not be in the concept, right? So all of them are already 0. So because you are applying this rule that only make those entries as 0 which are 1. Now since this is a negative concept, it means that I would never make any entry which is part of the concept, because if it were part of the concept, then it would not have been 0 in the then this would not have been a negative example. It's a little too much to take. Okay, I'm trying to explain it in a weird way, but the idea is this. See, if it were a negative example, right? If the concept had labeled it negative, even though you do not know the concept, right? So let us assume again, yeah, here. So let us say this is our data, and let us say this is our concept, right? So if this is our concept, then when a data point comes which is negative, we are sure that this will be 0, this will be 0, and this will be 0, right? Because otherwise the concept would have labeled it as positive. So if all of these are 0, and in your elimination you are only eliminating those weights which are 1, for which the x is 1, that means for that negative example maybe this was 1, this was 1, this was 1, or they could be 0, but what you are guaranteed is that these three will never be 0, right? Which means that in an elimination you would have set some of these to be 0, some of the unwanted ones to be 0, but the ones that you want will still be there. So that's the idea. Okay, and the same way in the promotion, what happens is that there was a positive example, which means that for that positive example one of these had to be 1, right? At least one of them. And you made a mistake. So now what you are going to do is you will bump up the weights, but you will, because you don't know the concept, you will bump up the weights for all those instances, all those attributes for which the value is 1, right? So you might incorrectly bump up the weights for something that does not belong to the disjunctive concept, which is fine, because hopefully they will get eliminated at some point. But what does happen is that you are guaranteed to bump up the weight of at least one of these three, because one of these three will be 1 in this case, right? So over iterations what will happen is that slowly all the unwanted ones get set to 0, and all the ones that we want will keep on increasing. All right, so at the end of the training, hopefully what will happen is that you would learn the weight that will be able to differentiate between the two types of data objects. Any questions? I'm sorry, can you say that again? Elimination, right. So what happens is elimination, where is that? So the idea of elimination is that whenever you make a mistake, that means your current weight vector called something positive when it was actually negative, right? So you set the way that all the entries in W that correspond to a 1 value in the X, right? Because what you know is that since this is a negative example, that means none of the useful entries that we want, none of the ones that are in the disjunctive concept will be 1. That means you will never set any of the ones that you really want to 0, right? But you will keep on setting the other ones to 0, right? So you will keep on eliminating the unwanted one. That question there?
Does this also tell that a particular attribute is more preferred to like other? For example, I have two attributes for validation.
Right.
And some cases dark is more preferred to like the others.
Uh,
If I have dark, that is more preferred to like me not having dark and having other.
right. So that's a good point. So what the question is that will Vino also tell you which attributes are more important in the discrimination? But it won't. The reason being that since we are assuming that your concept is disjunctive, right? So the disjunctive concept is not the true concept is not giving any preference to any attribute. That means that there is no point in sort of differentiating between the two. But in real settings, and we will see those in next week and from then on, is that yes, most of the algorithms will tell you which attribute is more important than others, right? But not this one, because the true one does not give that weightage. Yes, go ahead.
Why do we do promotion? Doing only an elimination to get it to the correct W.
No, so it could happen that at some point, see, you do want to eliminate, right? But you also want to promote because then you will quickly converge to your right answer. What happens is if you do not do any promotions, then after some training data, you would have unnecessary value, some of the unnecessary weights, you would have set them to 0. But but you might still have some of the unnecessary ones as ones because it depends on how much training data you have, right? But so what will happen is that at that point you might your Vino line might not be accurate enough. But if you're doing the promotion, then the effect of these might dominate the effect of others. That's why we do promotion and elimination both. All right. So to finish the discussion, the point that I want to make, and please go ahead and attempt the gradients quiz to make this more concrete in your mind, is that if you analyze this Vino algorithm, what you will see is that no matter what your concept is, it needs to be disjunctive, it will learn the true concept after making these many mistakes. Okay, so remember, this was our first argument. We were trying to come up with these bounds, right? So for different concept classes, we were trying to set this bound saying, okay, how many mistakes would I make? How many mistakes would I make at the worst case, right? So Vino lets you do that for disjunctive concepts, okay? So in general, it is k log base alpha, but if we set alpha to 2, then it is k log 2d. All right, that's actually exactly what the halving algorithm also does. But this algorithm, the good thing about this is that it is implementable and it is very efficient, right? You can write a code and you can run it very fast because there is no and the memory requirements are also small. You are not maintaining your version space or anything, right? So that's the beauty of this. Uh, and then you certainly can use other values of alpha and theta, but that's beyond our study here. Another thing that is beyond our study is that there are other implementations of Vino that work on other types of concept classes. So arbitrary disjunctions, which means they are no longer monotone. They could be other form as well. There is KDNF, disjunctive normal forms, which are of this form. So there have been many extensions proposed in literature. We won't look at those for this class, but if you're interested, you can look that up as well. All right, so I did have well, we'll do that in the next class. Any questions before we stop? Yes, go ahead. See, we start with ones, right? All W's are ones, and in promotions we are just doubling it. So it will always go up, up, up. There's one more question here. Yes.
The value of alpha is true because the attributes are binary or there's nothing more relation there?
No, yeah. The fact that attributes are binary is what drives this. So if they're not binary, you have to do something else. Yeah. All right. Thank you very much. I'll see you.